So here's an identity that I think would be considered by most people when they see it for the first time as something which surely has to be wrong. And this is 1 cubed plus 2 cubed plus 3 cubed plus and so on, you know, till n, and also cubed, is actually the same as just 1 plus 2 plus 3 and so on till n, and that's things squared. So clearly that looks wrong, but it's actually completely correct. Let's maybe check some values to just convince ourselves. So let's do the trivial case, n equals to 1, then you on the left hand side you just have 1 cubed, so 1, and on the right hand side you have 1 squared, so you could get 1 equals 1. Okay, so that's true. But more interesting is perhaps the case n equals to 2. Then on the left hand side you get 1 cubed plus 2 to the third, so this is 1 plus 8, so this is 9 on the left hand side. And on the right hand side you get 1 plus 2, and then, so that's 3, and then squared, so that's 9. So again, you get 9 on both sides of the equation. So it's looking good. I will not prove this identity. This is an easy induction proof. But what the true magic, of course, in this identity is this elegance, right? It just looks too good to be true. But the thing is, there's even more identities like this. So here's another one. 1 cubed plus 2 cubed plus 3 cubed, and so on, till n cubed. Now that's an interesting thing. I've already considered this here, but what if I do the same thing with fifth powers? So what about 1 to the fifth, plus 2 to the fifth, plus 3 to the fifth, and so on, till n to the fifth. Now the fun thing is, if I take just 1/4 of this, and 3/4 of this, and that's the same thing as 1 plus 2 plus 3, and so on, till n, this time cubed. So there you go, another identity of such a type. Now, the thing I want to talk about is that these kind of identities were understood long ago, like in the 1600s. So this is like really old observations which I'm discussing here. But Faulhaber has actually proved that whenever you consider such an expression, so a sum of consecutive integers starting from 1, and then having only odd powers, so this is what we're having here, right? Only power 3, which is odd, and only the power 5, which is odd. So if you have only odd powers, then it's always possible to express the value of these as a polynomial in just 1 plus 2 plus 3 and so on plus n. So here you have this, right? You can express these cubes as a polynomial in just the sum of the values, namely you square them. And here you have, it's more complicated. You have these third cubes, and here you have the fifth cubes, but again, you can express them as just a polynomial in 1 plus 2 plus 3 till plus n. This time it's the third power. So you see, you see this phenomenon here, and what I'll do in this video is I'll give you a complete proof why that thing is true. So let's just first write down all of this actually as a theorem. So first of all, we give a name to the sum. So I'll call this SLN. Will be just the sum from k from 1 to n of k to the L. Yeah, so this is just the same as 1 to the L plus 2 to the L plus 3 to the L and so on till n to the L. And yeah, so that's a sensible definition, I guess, for n at least 1. So that's just our name for these sums. And now the theorem by Faulhaber is the following. It says, suppose the exponent, which I called L here, is, well, at least 1, is odd, then there exists a unique polynomial, FL, in the rational polynomial ring. For the name of the variable, I'll be using z or z, such that 1 to the L plus 2 to the L plus 3 to the L and so on till n to the L is the same as FL of 1 plus 2 and so on till n. Yeah, so the statement is that whenever the powers are odd, then it's possible to express this sum as a polynomial just in 1 plus 2 plus and so on till n. So let's prove this, and maybe first let me show you that we already know FL for two values, right? I mean, F1 is pretty obvious, because if the exponent is 1, then you just have the sum 1 plus 2 plus 3 and so on till n. So that's just the same expression as you have here. So F1 of z is the identity, and F3 of z, well, I mean, I just shown you this example. Yeah, so if you just add all the cubes, you just have to square the sum of the integers. So this means that the f3 is z squared. And you know, if you want to go further, then to also say something about expressions like these, then you would also need the fifth power expression. So then you would need to compute f5. And I will not tell you what f5 is. I can just tell you that the polynomials will get more complicated as you go up in the powers L. So they're not as easy as these. Okay, but now let's prove this theorem. I'll show you a proof by Reuben Hersh, which I believe is the slickest proof, at least I have seen. It's really clever. So in order to get started, we need a little lemma. And the claim is that SL of n is a polynomial in n. So I can write SL, so by polynomial I mean rational polynomial, is an element of the polynomial ring in Z. And this is not obvious if you just look at the definition of SL. So especially if you look at it, like if you look at just this term, you see a sum, and the bigger n gets, the more summons there are. So this is not the format of a polynomial. And maybe if you look at this expression, it's more tempting to believe that this were a polynomial. But note that it's not just, like it might look like this is a polynomial in n, and this is like a polynomial of degree L or something like this. But it's not true, right? Because if n grows, if n, for example, would now go to n plus 1, it's not just that I plug in n plus 1 here for this n, right? We really get one more summoned. So it's not so obvious that this expression is a polynomial in n. So yeah, this lemma is an actual non-trivial statement. Now, this is easy to prove, and I will prove it, but I'll prove it later, because the fascinating thing about the proof is that we will actually not need to know what this polynomial is, nor really anything about it. All we need to know is that it is a polynomial. So let's prove this later. So let me just show you what it is good for to know that it is a polynomial. An interesting observation is that I can compute what SL of n plus 1 is very nicely from SL of n, because all that happens is once n increases is that I'm getting one more summand here, right? One more summand in the sum. So one more summand gets added here. So for SL n plus 1, all I get here is an additional summand plus n plus 1 in brackets to the L. So I know this expression. Good. And this holds for all n at least 1. But the fun thing is, now that I know that SL is a polynomial in n, and I have an identity which holds for infinitely many values, namely all integers, all positive integers, I know that this identity must actually hold for all values of n, even negative ones. Now this is based on the fact that SL is a polynomial in n, and like polynomial of degree m, as soon as you know something about m plus 1 values, this uniquely fixes the polynomial. So having this identity for infinitely many values means that no matter what degree SL is, even though we could totally determine what it is, but we don't need to do it. This means that this identity will hold for all values of n. Good. So this means I can actually say something about the value of SL at negative integers, which, if you look at this definition, it's really unclear what this would mean if n is negative. I would have to consider a sum from 1 till, a negative number. What does that mean? Should I somehow go through the numbers in reverse order? I don't know. We only use this identity here, this definition, for all the positive integers. And then we use the lemma that SL is a polynomial in n. So this means we know that these negative values, we can evaluate them. We have no indication that this formula would in some way be valid, because we're only using this for the positive values. But we certainly can plug in the negative values, and we can use this formula to figure out what the value is of SL at negative values. So let's do that. All I do is I will just replace n by n minus 1. So I'm just plugging in n minus 1 for n. So this is SL of n minus 1 plus, and then I get n to the L. And now I solve this for SL of n minus 1. Yeah, this is the same as SL of n minus n to the L. So this is the key identity. And now I can use this to say something about negative values of SL. Let's do it. We'll just do it some cases. So what about SL of 0. So this is easy to figure out. This means I have to plug in n is equal to 1. So this is the same as SL of 1 minus 1 to the L. So minus 1 to the L I can already write, minus 1 to the L, and I need to know what SL of 1 is, which is easy. In this case, this formula here is valid. So if n is 1, then I just get one sum, and so I just get 1 to the L. So this is 1 to the L, and this actually cancels, right? This is 0 always, no matter what L is. And okay, let's do SL of minus 1. Use the same formula, SL of minus 1. Now n is equal to 0, so it's the same as SL of 0, which I already computed is 0. So this is the same as 0 minus n to the L, and n in this case was 0. So this is minus 0 to the L, and since I'm always assuming, also in Faulhaber's theorem, this was an assumption that L is at least 1, this safely is also 0 all the time. This looks pretty boring, but it'll get more interesting now. So SL of minus 2. So now n is minus 1. So this is the same as SL of minus 1, which I just computed to be 0. Minus, okay, and now something happens. So this is n was minus 1. So this is minus 1 to the L. So you see, finally something is happening. Let's do SL of minus 3. Okay. So SL of minus 3. So this time now n is minus 2. So I get SL of minus 2, which I've just computed. So this is minus 1 to the L. Minus, and now remember, n was minus 2. So minus 2 to the L. Okay, so now let's do SL of minus 4. Sorry if this seems like it's getting a little bit boring, but you'll see a pattern soon. So if I want to know what minus 4 is, I have to plug in minus 3. So I get SL of minus 3, which I've just computed, so I can just copy this. This is SL of minus 3. And then I get minus 3 to the L. Minus 3 to the L. And you know, I think now we see a pattern, right? And we guess the following formula. SL of minus n, so n will at least be 1 as before. Then this is surely the same as the sum from k from 1 till, okay, apparently n minus 1 of minus k to the L. Yeah, and okay, so now proper mathematicians, as we are, we would now prove that this formula holds by induction. This is an easy induction proof. Basically, I mean, you've just developed this using induction. So you just need to use this formula. But yeah, I will not do it because, I mean, this is really, I think it's pretty obvious now that this is fine. Okay, so now we have a very nice formula for SL at the negative integers. And let me stress again, just to be completely clear here. If we just use the definition here, there's no clear meaning to negative if we plug in negative values for n. You know, of course, we can argue what this meaning of the sum should be, but that's a bit dodgy. So this really is only properly defined for positive values. And then we can do all of this just under the assumption that just using that SL is a polynomial. So this justifies all of these computations. Good. Now we finally use the assumption that L is odd. Right? We haven't used this so far. Suppose L is odd. Now, the reason why this is relevant is because this allows us to find out what the sign is here. So since L is odd, I know that this actually simplifies to SL of minus n is the same as minus the sum from k from 1 to n minus 1. And now, since L is odd, in all of these I get a negative sign, right? This is k to the L, but all of these with a negative sign. So this cancels this one. So I actually get plus. And this means that SL of minus n is actually exactly the same as SL of n minus 1, just comparing definitions. So I have a very, very interesting identity. SL of minus n is the same as SL of n minus 1. So this is very interesting. So we have some kind of a weird symmetry between negative values and positive values, but it's a little bit off. So the next trick is, remember that this is now an identity of polynomials. It's valid for all n at least 1, right? This was my assumption here. I've used this here. But again, these are infinitely many values. So this is actually true. This is an identity which is true for all values, right? Because again, SL is a polynomial. So in particular, I can actually just replace n by n plus 1/2. Let me stress again, this is only possible because we know that SL is a polynomial. If we just had the combinatorial definition of SL from the beginning, you know, it'd be a completely crazy thing to just take a sum till n plus 1/2, right? What does this even mean? But we don't have these problems because we know that SL is a polynomial. So we can plug in n plus 1/2. Okay, so I'll just do this. So I'll just replace n by n plus 1/2. So that I get n minus n plus 1/2. Okay, and this is the same as SL of n plus 1/2 minus 1. Okay, and I simplify this. This is SL of minus n minus 1/2 is the same as SL n of now plus 1/2 minus 1 is minus 1/2. Okay, and now that's interesting because I see there's kind of a term minus 1/2 twice here. And here I just have minus n and n. So this really motivates the following nice definition. I define TL of z as a new polynomial, and this is SL of z minus 1/2. So what is TL? Well, since SL is a polynomial, I know that TL is a polynomial too, because really what's happening, if you replace z by z minus 1/2, this just means we shift, right? And the graph just shifts by half a unit. So I also know that TL is a polynomial in. So part of my lemma was to know that SL is a polynomial with rational coefficients. Just because 1/2 is also rational, I also know that TL is a polynomial with rational coefficients. And given this definition, and I've just copied this mysterious shift by minus 1/2, I now get the identity that TL satisfies minus n equals TL of n. Okay. So this, of course, just means that TL is an even function. Yeah, remember again, so strictly speaking, I only have this identity up here from the beginning. I had this only for integers, but because all of these are polynomials, I know that an identity which holds for infinitely many values must hold for all values. So this really holds for any n being a rational number or even a complex number. So therefore, this means that TL is an even function. But TL is also a polynomial, and you know that a polynomial which is a polynomial only in even powers. So TL, of course, it lies in the polynomial ring in Z, but actually it even lies in the subring generated by the square of Z. Yeah, this is a subring of Q of the polynomial ring. Yeah, this is just the statement that TL is a polynomial, but it's also an even function. Good, and now I'm basically done. This is the main trick of the whole proof, because now I can compute what SL was. Remember, SL of Z was actually the same as TL of Z plus 1/2. Yeah, this is just undoing the coordinate transform here. I'm just shifting. I've shifted here by minus 1/2. Now I'm shifting by plus 1/2. And since I know that TL was part of this polynomial ring in the even powers, I now deduce from this that SL actually lies in the polynomial ring in the variable Z plus 1/2 squared inside of the polynomial ring in Z. Yeah, this is just observing that SL can be expressed as TL of Z plus 1/2 plugged in, but TL lies in the subring of even powers. So I learned that SL lies in the subring of even powers of Z plus 1/2. Okay, and now we do remember the following classical trick. I think it's often attributed to Gauss because of this anecdote, but really, of course, it was known much earlier, namely that 1 plus 2 plus 3 plus 4 plus n. There's this classical trick to compute what that is. I'll just repeat it, even though I'm sure you know what I mean. You just write the same numbers under these, but in the opposite order, plus n minus 2, and so on, plus 2 plus 1. And now every column has the total sum n plus 1, right? This is n plus 1, n minus 1 plus 2, this is n plus 1, n minus 2 plus 3, this is n plus 1, this is n plus 1. So all the columns here have the value n plus 1. So if I sum all of these terms, I get the value n plus 1. Then because I have n columns, I get this n times, and because now actually every number occurred twice, and I'm only interested in the sum up here, so I'm not interested in these terms, I have to divide this by 2. This is, you know, a classical well-known identity. But the trick is, let's complete this square in this term here. What I get here is 1/2 n plus 1/2 squared minus 1 divided by 8. So let me just you know, so that we don't get confused, let me double check this. Let me just undo this bracket. So this is 1/2, and now binomial formula n squared plus 2 times the first thing times the second. So this is n, and then the square of the last term, this is 1/4, so minus 1/8. If I simplify this is 1/2 n squared plus n plus 1 divided by 8 minus 1 divided by n is 8. So I get exactly this expression, which clearly is the same one as I have up here. So completing the square gives me this identity here. But now I note that this term here, of course, looks precisely like this term. Remember what we had to prove. It was the claim that if I want to evaluate this term, which is SL of n, right? This thing here, this is, using our notation, SL of n. If I want to evaluate this, the claim is that this is a polynomial in 1 plus 2 and so on till n. Good, so I'm plugging in a positive integer for n, which means that up here, when I evaluate this polynomial, I plug in a positive integer. So then I know that SL is a polynomial of, when I plug it in, n plus 1/2 squared, but n plus 1/2 squared here by a linear transformation is the same as this sum. And this is the proof. This gives me the full statement. That's it. Yeah, I mean, if you want to be more precise, what you can now solve this little equation here for n plus 1/2 squared, which is easy, right? I mean, you just add 1/8 to this expression, then multiply everything by 2, and then you have an explicit expression rewriting this term in terms of this term. Yeah, and that's the proof. That's super slick. And what I particularly like about it is this very elegant use of the polynomial property. Good. I still owe you a lemma, right? I still owe you the lemma to show that SL is actually a polynomial in n. Okay, so let me just write the lemma again. So the statement is that SL of n is a polynomial in n, a rational polynomial. So I can also write SL is an element of the rational polynomial ring in the variable z. So, and the proof is actually very nice and not difficult at all. I just wanted to move it further back so that we don't get the wrong impression that we would have to know what polynomial it is. We just need the polynomial property for the previous part of the proof. So the proof is as follows. I'll just write n plus 1 to the l plus 1 minus 1. And I just write this as a telescope sum. So I go from 1 till n of k plus 1 to the l plus 1 minus k to the l. Yeah, so this is a telescope sum. So why does this identity hold? Well, you know, so for k equals to 1, we get 2 to the l plus 1. Sorry, I forgot. Plus 1, 2 to the l plus 1 minus 1 to the l plus 1. And this minus 1 to the l plus 1, 1 to some power will just be 1 always. This will actually be this one. Okay, and here we have 2 to the l plus 1, but once k is 2, we get here a minus 2 to the l plus 1. So this will cancel with this 2 in the previous summand. We also get a new term, 3 to the l plus 1, but once k is equal to 3, we get a minus 3 to the l plus 1, so that again cancels with this 3 we found, and we get a 4 to the l plus 1, and so on. And all these terms cancel. This is the trick of a telescope sum. Except for this cancellation doesn't work always in the first and the last term. So we already had the last term, and we also get the top term. The top term is where k is equal to n, and then we get n plus 1 to the l plus 1, so this is this term here. And this term is the one which cancels with the one from the previous summand. Okay, so this is just a telescope sum. Now I use the binomial formula, k to the n. So this is the sum, I'll call this m, going from 0 till n l plus 1, or binomial coefficient l plus 1 over m of k to the m, and then I get back here minus k to the l plus 1. Yeah, so this is an individual sum. Good, but now actually I discover that the summand for m is equal to l plus 1 is just what's written here, yeah? Because if m is l plus 1, then I get l plus 1 over l plus 1, which is 1, and k to the l plus 1. So actually this subtraction is just the same thing as removing the top summand in this sum. So this is totally the same as the sum from 1 to n, and then from m from 0 only to l, because I'm removing the last summand, to l plus 1 over m times k over m. Okay, and now I discover that actually all of these terms here, the only thing which depends on k is this thing here, and here I have this sum over k, so I can actually swap the order of summation. I mean, this is harmless because these are only finite sums anyway. So I get the sum from 0 to l of l plus 1 over m, and now an additional sum. Now this sum goes from 1 till n of k to the m. And of course I recognize what this term is, right? Because this is just a special instance of our function SL, right? Well, in this case SM. So this is the same thing as the sum m goes to 0 to l of l plus 1 over m. And this is just s, and the power is m, sm, and the last value is m, so this is just smn. Okie dokie. And this is the proof. Because what does this proof show us? So everywhere here L was arbitrary. I mean, L actually should maybe be at least 0, but so if I want to show that something is a polynomial in n, I might just as well show that it's a polynomial in n plus 1, because again this is just shifting a polynomial by, this time, a unit. This doesn't destroy or disturb the property to be a polynomial. Okay, and so here I see that all the powers of n plus 1, all of the powers, you know, this can be regarded as a 0th power, that they can be expanded in the functions Sm of n. Good, but this means in reverse, I can also rewrite all of these terms Sm, you know, like always the highest summand, as a linear combination of these terms. You know, in order for this to work, all I need to know is that the coefficient in front of the highest term in here, so which is m is equal to l, is non-zero, which, however, it is. So, you know, I can always solve this for Sm and express this, you know, if I just isolate the highest summand, yeah? And so, of course, we could, you know, be more precise here and actually compute what these polynomials are, just we don't need it for the proof. It's completely not necessary.